Welcome back, dear listener, to Sleep Theory TV. Tonight you can close your eyes and let the world around you fade into stillness. Breathe slowly, deeply, in and out. As you drift towards sleep, let us journey back, far back, beyond the Earth, beyond the Sun, beyond even the galaxy itself. We travel to the very beginning, to the origins of the universe. The story of Earth begins not with Earth itself, but with everything. To understand the birth of our planet, we must go back to the moment when time and space themselves first unfurled. Scientists call this moment the Big Bang. It was not an explosion in the ordinary sense, not a fireball bursting in the void, but rather the rapid expansion of space itself, carrying matter and energy outward. 13.8 billion years ago, all that we know, the galaxies, the stars, the atoms in your body, was compressed into a single, unimaginably dense point, a point smaller than the tiniest particle we can imagine. And then, in an instant, it began to expand. The early universe was hot, searingly hot, so hot that matter as we know it could not yet exist. Instead, it was a thick, swirling sea of energy, of fundamental particles in constant motion. As the universe cooled, these particles began to combine. The first atoms formed, hydrogen, the simplest, and helium, the second. These light elements would become the building blocks for everything else to come. Imagine drifting now through this young universe. There are no stars yet, no planets, only vast clouds of hydrogen and helium gas. It is dark, silent, and endless. Slowly, gravity begins its patient work. Over millions of years, these clouds gather together, drawn inward by their own weight. Denser and denser they become, until deep within their hearts a spark ignites, nuclear fusion begins, and the first stars are born. The stars were the universe's first great alchemists. Inside their blazing cores, hydrogen fused into helium, releasing light and warmth. As stars aged, some fused even heavier elements: carbon, oxygen, iron. When the largest stars reached the end of their lives, they collapsed and exploded in brilliant supernovas. In those final violent moments, the heavier elements that Earth would one day hold, magnesium, silicon, gold, uranium, were created. Every atom of iron in your blood, every atom of calcium in your bones, was born in the heart of a dying star. We are, in the truest sense, stardust. Pause now and imagine these supernovas scattering their treasures across the galaxy. Clouds of enriched gas and dust drift through space, ready to one day gather again, to form new stars, new planets, and perhaps worlds like our own. Billions of years pass in this cosmic ocean. Galaxies take shape, spiraling and stretching. Stars are born, live out their brilliant lives and fade. Amid all this, one small arm of a galaxy we now call the Milky Way begins to swirl with potential. Within it, a new star is preparing to shine, our Sun. But before the Sun's light can rise, before the Earth can take shape, the stage must be set by countless cycles of cosmic birth and death. The universe is patient, and in its patience, it builds. As you breathe slowly, let yourself feel the vastness of time. 13.8 billion years. a span so great it dwarfs human imagination. Yet here we are, contemplating it, floating in thought through an ancient cosmos, drifting toward the moment our own solar system began. The story of Earth is not rushed. It unfolds like a gentle tide, with each moment that passes. With each breath you take, we move slowly forward in cosmic time. The early universe, after the first stars began to shine, was still a restless place. Gravity was weaving structures out of the endless gas and dust. Stars gathered together in families, forming galaxies. These galaxies drifted apart as space itself stretched. Yet within each one, life and death of stars continued ceaselessly. Imagine a dark night sky, far emptier than the one we know. Few stars twinkle there. The young cosmos is sparse compared to the fullness we see today. Over time, more stars ignite, clusters grow, galaxies form their elegant arms, and the heavens gradually fill with light. Our own galaxy, the Milky Way, was forming during this time. Picture it slowly spiraling into shape. A collection of hundreds of billions of stars, dust and gas, dancing to the invisible rhythm of gravity. Somewhere within its swirling arms, long before Earth existed, generations of stars lived and died, each one enriching the cosmic material that would one day gather to form our solar system. It is humbling to think that our world, and all the life upon it, required not one star, but many. It took countless stars to build the ingredients of Earth. Without their cycles, there would be no iron to form Earth's core, no silicon to shape its rocks, no oxygen to fill its skies. Let us pause here. Imagine the silence between galaxies. Imagine the vastness, the almost unimaginable emptiness, where distances are measured not in miles or kilometers, but in light years. The distance light travels in a year. A single light year is nearly 6 trillion miles, and yet galaxies are separated by millions of them. In that immense gulf, stars are like tiny beacons scattered across a boundless ocean. And yet, even in this enormity, the story that leads to Earth is unfolding. Every explosion of a star, every drifting cloud of gas, every merging of galaxies is another step in the great chain of events that will eventually lead to the blue planet you call home. Time passes slowly in this story. Stars are born over millions of years and die after billions. Galaxies drift and evolve over unimaginable ages. Compared to this, a human life is but a flicker, a spark in the darkness, and yet it is within our brief spark that we are able to reflect on all of this. Now, imagine floating through a stellar nursery, a place where stars are born. Vast clouds of dust and gas stretch for light years, illuminated here and there by the glow of newborn stars. In the quiet, particles of dust collide and cling, forming grains, then pebbles, then clumps of matter. What you are seeing here is the very beginning of the same process that will form planets. Though we are still billions of years away from Earth's birth, the pattern is clear. The universe is laying its foundation. Element by element, structure by structure, it is preparing for what is to come. As you drift deeper into this cosmic story, let the immensity of time and space wash over you like a calm tide. Let the numbers, the billions of years, become less about counting and more about feeling an endless expanse, a gentle eternity in which everything unfolds. And somewhere, in the quiet arm of a spiral galaxy, a small star is waiting to ignite. That star will be our sun. Its light will one day warm the Earth. Its gravity will hold the planets in place, and without it we would not be here to wonder. But before we arrive at the sun's birth, let us linger a little longer in the grand star-filled canvas of the universe. The stage must be set. The actors, stars, dust, galaxies must all play their roles before the curtain can rise on the solar system. In the quiet expanse of deep time, the universe is a patient artist. With every passing million years, it brushes faint strokes of light and matter across the canvas of infinity. We are still at the very beginning of the story, yet the seeds of Earth are already being prepared. The first stars that lived and died gave the universe its variety of elements. But these early stars were not alone. They gathered into clusters, drifting together under the steady hand of gravity. Over time, these clusters grew larger and more complex, swirling into the spiral and elliptical shapes we now know as galaxies. Our home galaxy, the Milky Way, was among them. In its earliest days, it was not the graceful spiral we see in images today. It was raw and chaotic. Clouds of gas collided, stars formed in bursts, and great streams of material stretched across space like rivers of light. As the Milky Way settled, it began to form the familiar arms we know now. Spiraling waves of stars and dust, curving outward from a dense center. Imagine standing on the edge of that spiral, looking inward. A soft river of light would stretch across the darkness, glowing faintly with billions of stars. This is the home of our sun, though at this moment the sun does not yet exist. But the matter that will one day make our sun and our Earth is already here, drifting through the galactic arm. It waits as dust, it waits as gas, it waits as scattered fragments from generations of dying stars. Pause and think of this. The calcium in your teeth, the carbon in your skin, the oxygen you breathe, the iron that carries life through your blood. All of it was forged long before Earth itself. These atoms traveled the galaxy, carried by winds of exploding stars, before finding their way to the place that would become our solar system. Each in time, about 4.6 billion years ago, one vast cloud of gas and dust within the Milky Way began to collapse. Gravity pulled it inward, gathering it tighter and tighter until it flattened into a spinning disk. At its center, matter clumped together, grew hotter, and blazed to life. Our sun was born. But before we arrive at that turning point, let us linger still in the wider cosmos, for the Earth is not an isolated creation. It is part of a much grander cycle, one that stretches far beyond our planet and even our galaxy. Consider the great scale of time. The universe has existed for nearly 14 billion years. Earth, by comparison, is only 4.5 billion years old. This means that for nearly 2/3 of cosmic history, Earth did not yet exist. Entire galaxies formed, stars lived and died, and countless cosmic dramas unfolded. all before the ground beneath your feet was even imagined. Think of how long that is. If the age of the universe were compressed into a single year, the Earth would not appear until September. Humans would not appear until the very last few minutes of December 31st. And all of recorded history would be only a fleeting instant before midnight. This perspective is not meant to make us feel small, but connected. We are part of something vast, something ancient. The atoms of our bodies are older than the Earth itself. The story of Earth is also the story of us. And the story of us is inseparable from the story of the universe. Now, let us drift back again to those glowing clouds of gas. Imagine floating weightless through a stellar nursery. Great curtains of colour shimmer in the distance, gases glowing softly in hues of red and blue. Here, stars are beginning to take shape, their gravity pulling matter into dense knots. You hear nothing, for space is silent, but you can almost feel the slow gathering of energy, the quiet promise of light. These nurseries are the cradles of suns, and one of them, long ago, became the cradle of our own. The Earth's story is still waiting to begin, but already the universe has given us everything we will need. The elements are ready, the galaxy is stable, the conditions are falling into place, and so, with time as our guide, we move forward, toward the moment when the sun will blaze into being, and the dust of stars will begin to gather into worlds. Close your eyes once more, and let us drift forward in time. The universe has already painted the backdrop. Billions of years of stars, of galaxies, of dust and light. The elements we need are ready. Now the story of Earth draws closer. The curtain lifts upon a new scene, a new beginning, the birth of our solar system. About 4.5 billion years ago, in a quiet arm of the Milky Way galaxy, a vast cloud of gas and dust drifted silently. This cloud was no different from many others scattered across space. But within it lay the potential for something extraordinary. Within it, our sun would be born. Around it, the planets, including Earth, would one day take shape. The cloud was made mostly of hydrogen and helium, the simplest and most abundant elements. But sprinkled within were heavier atoms: carbon, oxygen, iron, silicon, magnesium. These were the gifts of earlier generations of stars, scattered by ancient supernovas. Without them, the rocky worlds like Earth could not exist. Something disturbed this cloud. Perhaps it was the shockwave of a nearby supernova, the dying breath of a massive star. Perhaps it was the natural ebb and flow of the galaxy itself, stirring the cloud into motion. Whatever the cause, gravity began its patient work, drawing the gas and dust inward. Slowly at first, and then more insistently, the cloud began to collapse. As it collapsed, it spun. Just as a skater spins faster when pulling in their arms, the contracting cloud whirled more quickly as it shrank. The material flattened into a disk, wide and thin, with most of the mass gathering at the center. There, pressure and heat built until, at last, nuclear fusion ignited. The sun had been born. Its light pierced the darkness. For the first time, the heart of this cloud blazed with brilliance, and all around it the leftover gas and dust swirled, forming the great disk we call the solar nebula. From this nebula, the planets, moons, asteroids, and comets would be assembled. Imagine drifting now through that young solar system. At the center is a star, golden and fierce, its newborn light pushing back the shadows. Around it, the disk glows faintly, filled with swirling streams of dust, grains of rock, and frozen particles of ice. It is not yet a peaceful place. Collisions are constant. Matter clumps together, breaks apart, and clumps again. The solar system is noisy, chaotic, and alive with creation. Over millions of years, small grains of dust collide and stick together. At first, they are tiny, smaller than sand, but slowly they grow into larger and larger bodies, pebbles, then boulders, then mountain-sized chunks of rock. These are called planetesimals, the building blocks of planets. Their collisions are not gentle. They slam into each other with violent force, breaking apart as often as they merge. But gravity is persistent, always pulling matter together again. The larger a body grows, the stronger its gravity becomes, pulling in even more material. In the inner regions of the solar system, close to the newborn sun, the heat is intense. Here, only metals and rocks can survive. Lighter materials, like water and ice, are driven outward by the sun's warmth. And so, it is in this inner region that the rocky planets, Mercury, Venus, Earth, and Mars, will form. Farther out, beyond a boundary called the frost line, it is cold enough for ices to remain. There, massive planets of gas and ice, Jupiter, Saturn, Uranus, and Neptune, begin to gather. These giants will shape the solar system with their immense gravity, flinging smaller bodies inward and outward, clearing vast paths through the nebula. But here, near the warmth of the young sun, something special is happening. Dust and rock are coalescing into a growing sphere, a world that will one day become Earth. It is not alone. Other planetesimals crowd this region, competing, colliding, and merging in a chaotic dance. Some will be destroyed, others will be absorbed. The process is violent, but it is also creative. The Earth, though still young, is beginning to take shape. Breathe deeply, in and out. Imagine yourself drifting in that young solar system where time stretches across millions of years. Everything moves slowly, yet the changes are immense. This is the place where planets are being born. The solar nebula, the great swirling disk of dust and gas around the sun, is vast. It stretches for billions of miles in every direction. From its glowing center comes the light and heat of a newborn star, pulsing gently across the disk. This light is both life-giving and destructive. Close to the sun, the heat is so fierce that fragile ices and gases cannot remain. Only rock and metal endure, and these are the seeds from which the inner planets will grow. Farther away, where the sunlight is weaker and space is colder, a different story unfolds. Here, ice crystals remain stable, adding to the mass of the forming planets. It is in this distant realm that giants like Jupiter and Saturn begin to emerge, massive enough to dominate their surroundings. Their gravity strong enough to shape the fates of countless smaller worlds. But let us return to the inner regions of the disk, where Earth's journey is beginning. At first, there is nothing more than a haze of dust. Tiny grains drift together, sticking through faint electrical charges, like static clinging dust motes in the air. These particles collide again and again, gradually building larger clumps. What begins as a whisper of matter becomes pebbles, then rocks, then great boulders that tumble silently through the disk. As the millions of years pass, these rocky bodies collide with greater force. When they strike, some shatter into fragments, but others fuse together, held fast by gravity. This process, known as accretion, is the slow but steady path by which planets are born. Now, imagine looking down on this cosmic workshop. Countless planetesimals, the building blocks of worlds, drift and collide, a dance of creation and destruction. Some are small, only a few miles across. Others grow larger, mountain-sized, then continent-sized. Slowly, very slowly, the winners of this competition emerge. The larger a body becomes, the stronger its gravity, and the more material it can draw to itself. It is survival not of the fittest, but of the largest. Among these growing worlds is one that will become Earth. At this stage, it is far from the blue, life-filled planet we know. It is a barren rock, a sphere of molten stone, constantly bombarded by impacts. Each collision releases enormous energy, heating its surface, reshaping its form, and adding to its mass. But Earth is not alone. Around it, other protoplanets are also forming. Some are smaller, some are rivals nearly as large. For a time they coexist, orbiting the young sun in crowded lanes. Yet their paths are unstable, and sooner or later they collide. The solar system is a place of chaos, and only a few worlds will survive this violent youth. The sun, though young, exerts its own influence. Streams of charged particles flow outward from its surface, creating a solar wind that pushes the lighter gases away. Hydrogen and helium, abundant in the nebula, are driven outward, swept into the far reaches of space. This is why the inner planets remain small and rocky, while the outer planets grow massive and gassy. The sun shapes its children according to distance. Meanwhile, Jupiter, the giant among planets, is already forming far from the sun. Its immense gravity acts like a cosmic shepherd, tugging at nearby planetesimals, scattering some inward toward the young Earth, and flinging others outward into the cold depths of space. The presence of Jupiter ensures that Earth's history will be marked by countless impacts from comets and asteroids, bringing both destruction and perhaps the essential ingredients of life. Now, drift closer again to the place where Earth is forming. Picture it not as a finished world, but as a growing embryo of a planet. Its surface is molten, glowing with the heat of impacts. Volcanoes erupt constantly, spewing gases into the forming atmosphere. Oceans do not yet exist. Life does not yet stir, but the foundations are being laid. Every collision delivers more material. Iron, nickel, silicon, oxygen, all are added to the young Earth piece by piece. Slowly the planet differentiates. Heavy metals sink inward, forming a dense, molten core. Lighter materials rise, forming a mantle and a primitive crust. Already, the blueprint of Earth is emerging. It is important to pause here and reflect. What feels to us like violent chaos, the endless collisions, the fire, the molten seas, is in truth a natural process of creation. From disorder, order will eventually arise. From chaos, harmony will emerge. The solar system is sculpting itself into balance. Millions more years will pass before Earth becomes recognizable. For now, it is just one among many rocky worlds, jostling for survival in the crowded lanes around the sun. Yet it carries within it the promise of oceans, of continents of life, and of minds that will one day gaze back at the stars and wonder. And so, we float here in the dawn of the solar system. Dust becomes rock, rock becomes planetesimal, and planetesimal becomes planet. The sun shines steadily at the center, a golden heart beating life into its newborn family. Around it, the planets begin their long journey, each finding its path, each carving its destiny. Imagine drifting in silence. You are weightless, floating among the swirling clouds of the young solar nebula. All around you, endless streams of gas and dust curl and spiral, pull gently toward the newborn sun. The light of the sun is soft but steady, golden and young, reaching out into the disk that will become the solar system. Breathe in, breathe out. You are floating at the beginning of worlds. The disk is vast, so large that it would take millions of Earths lined side by side to stretch across it. Yet it is delicate too, a thin veil of particles spread across space. From a distance, it looks like a hazy ring of light, but up close, it is filled with detail. Tiny grains of rock and ice drift like smoke. They tumble, they collide, they cling together, then drift apart. It is a slow, patient dance that will continue for millions upon millions of years. At first, the particles are unimaginably small, microscopic specks born from the remains of older stars. Some are fragments of carbon, some are shards of silicate rock. Others are frozen crystals of water, methane and ammonia. Though tiny, they are the seeds of planets. Collisions are constant in this swirling disk. Each time two grains touch, they may stick together through electrostatic forces. Imagine dust motes in a sunbeam clinging to one another. Over time, these clumps grow. They become pebbles, then stones, then rocks as large as mountains. Each collision adds mass, and with mass comes gravity. Gravity is the great sculptor, the invisible hand guiding the dust into something larger, something rounder, something we would one day recognize as a world. The process is slow. From our perspective, it feels timeless. But in the language of the cosmos, these are the first rapid steps toward planetary birth. Within a few million years, the solar system is filled with planetesimals. Irregular bodies, some a few kilometers across, others hundreds. They drift like silent wanderers, each following its own path around the sun. But they do not stay separate for long. Their paths cross, their orbits intersect, and when they meet, the results are spectacular. Two small planetesimals collide and shatter into fragments, scattering debris across space. But sometimes they fuse, forming a larger body, their masses combined. Over time, the larger bodies attract more and more material, growing stronger, pulling in whatever drifts nearby. In the inner solar system, close to the sun, the rules are different than in the cold outer reaches. Here, the heat strips away light gases and vaporizes ices. Only rocks and metals endure. And so the inner planets are destined to be small and solid, Mercury, Venus, Earth, and Mars are the children of this fiery zone. Their foundations are stone, their hearts are metal, their surfaces born from collisions and fire. Farther out, beyond the frost line, the story changes. There, water ice and frozen gases are safe from the sun's warmth. Planets can grow far larger, their icy cores gathering enormous envelopes of gas. These become the giants, Jupiter and Saturn, Uranus and Neptune. Their vast size ensures that they dominate the outer solar system, shaping the orbits of countless smaller bodies with their overwhelming gravity. But our focus remains here, near the Sun, where Earth's destiny unfolds. Among the countless planetesimals, one is beginning to stand out. It is larger than most. Its surface glows with the heat of impacts, for it is constantly bombarded by smaller bodies. With every collision, it grows heavier, stronger, more stable. Piece by piece, rock by rock, it is becoming a planet. Still, the early Earth is not alone. Other protoplanets crowd its orbit. Some are rivals nearly as large. Their paths are unstable, and eventually their journeys will end in violent collisions. Earth may swallow them, or perhaps it will itself be swallowed. The young solar system is chaotic, unpredictable, and filled with destruction. Yet out of this destruction, creation thrives. Imagine now the view from the surface of this young Earth. Though no land or ocean exists yet, let your mind's eye wander across its molten plains. Rivers of lava glow in the dim light. Meteorites streak across the sky, striking with force so great that seas of rock boil. Volcanic eruptions spew gas into a forming atmosphere, a blanket of steam and ash. There is no blue sky yet, only a hazy red-orange glow beneath a churning sky. It is not the Earth we know. It is a world in the making. And above this fiery surface, the solar nebula still surrounds it, filled with drifting debris. Some of this debris will strike Earth, delivering new materials. Some will pass by, pulled away by the gravity of other worlds. The young Earth grows heavier with every passing moment, fed by the endless rain of cosmic dust and stone. Over time, Earth begins to change from the inside. Its heavy elements like iron and nickel sink downward, forming a dense metallic core. Around this, lighter silicates rise upward, forming the mantle. At the surface, the lightest materials create a primitive crust, fragile and unstable. Already, Earth is layered, its structure defined by the forces of heat and gravity. This differentiation is more than just structure. It lays the foundation for the magnetic field, for volcanic activity, for the tectonic shifts that will one day shape continents and oceans. The Earth is preparing itself, though it does not yet know it, for the story of life. But at this moment, the Earth is still young, still fragile, still one world among many in a crowded solar nursery. Around it, countless other bodies drift. Some will become planets, some will be consumed, some will be hurled into the distant reaches of space. The stage is not yet settled. The play is still chaotic. Yet slowly, order begins to emerge. The sun's light clears away the remaining gas, blowing it outward into interstellar space. The disk thins. The planets, now larger and more stable, begin to settle into orbits. The violence of formation is not yet over, but the outlines of the solar system are beginning to appear. The sun burns steadily at the center, a golden heart. Around it, Mercury, Venus, Earth, and Mars are forming from rock and metal. Beyond the frost line, the giants are swelling, gathering gas and ice into their immense forms. Between them all lie belts of debris, fragments of creation that never found a home. The solar system is no longer just a swirling disk of dust. It is becoming a family of worlds, and among these worlds, one will become the cradle of oceans, of continents, of forests and skies. One will hold the story of life. That world is Earth. Settle in, breathe slowly, in and out. Imagine that you are floating again, beyond weather, beyond clouds, beyond the familiar blue, drifting through the quiet beginning of the world. Tonight we stay close to home. We will watch the young Earth take shape. We move through time as if it were water, gentle and unhurried, and we observe how a clump of dust and rock becomes a living, breathing planet. The clock that counts Earth's age begins ticking about 4.54 billion years ago. That is where this chapter begins. Within the first tender moments after the sun's birth, when the solar nebula still hummed with motion and the process of planetary assembly had just begun. In that slow, patient nursery, gravity was the master craftsman. Small grains met and clung. Clumps formed. Clumps became boulders. Boulders became planetesimals. Planetesimals, through a billion tiny collisions, grew into protoplanets. One of these protoplanets will become Earth. Imagine the space around the newborn sun. A thin sunlit disk of gas and dust that stretches into vast, cold darkness. The inner part of that disk is hot and bright. Here, only the hard materials remain. Iron, nickel, silicate rock, and other refractory minerals. Each particle in that inner disk carries an ancient story. The remains of older stars, the fragments of supernovae. They drift and occasionally meet. When they meet, sometimes they stick. There is no hurry in these early meetings. Collisions are gentle at first, governed by static electricity, by slow drifting. Over time they become more forceful. As bodies grow, their gravity grows with them. A small clump, by chance, becomes a little larger, and then it becomes good at gathering more. This runaway growth is how the first truly large bodies form. Over the course of a few million years, a crowd of planetesimals becomes a family of protoplanets. Irregular, heavily cratered survivors in an environment shaped by constant impacts. Now, picture one of those protoplanets in slow motion. It is still irregular, lumpy, covered in the scars of collisions. Each impact delivers heat as well as material. The friction of accretion, the energy of impacts, and the decay of short-lived radioactive isotopes, especially aluminum-26 and iron-60, work together to heat the interior. Heat is the hidden sculptor of a young world. As temperatures climb, materials soften, then melt. The rock becomes fluid and mobile. This is the beginning of planetary differentiation. Differentiation is the great sorting process. Heavy elements sink. Lighter elements rise. Iron and nickel, denser than the surrounding silicate rock, migrate downward, drawn by gravity through a partially molten mantle. What was once a chaotic mixture separates into layers. At the center, a metallic core forms, a dense, spinning heart. Around it, a silicate mantle solidifies and convects. At the top, a thinner cooling shell begins to form a primitive crust. This layering, core, mantle, crust, is the structural blueprint of the planet we will come to know as Earth. Think of the core forming like beads of mercury falling through syrup. Each bead coalesces with others, forming a larger, heavier pool. The process generates heat as material moves. The core grows hot and begins to separate chemically from the surrounding rock. This organized interior is crucial. It allows convection in the metallic core, which later creates a magnetic field. That magnetic field will become a protective shield, guarding the planet's surface from charged particles streaming from the sun. For now, however, the core and mantle are young and turbulent, still settling into their long-term rhythms. As the interior evolves, the surface tells a different story, one of fire and red glow. Early Earth is therefore a place of magma oceans. Large impacts deliver so much energy that they can melt substantial regions, sometimes creating global-scale molten layers. Imagine the surface as a searing ocean of silicate liquid, glowing under a smoky sky. In that molten state, heavier crystals sink, lighter minerals float. Yet another process of separation that helps sculpt the evolving crust. Over time, patches of the surface begin to solidify. These solid plates, fragile at first, form the first crustal rafts. At the same time, the young sun continues to push gas outward with a vigorous solar wind. This wind helps clear away the leftover nebular gas that would otherwise blanket the newborn planets. The clearing of gas is a quiet but decisive transition. It means that the inner worlds are left to evolve without a thick primordial envelope of hydrogen and helium. The atmosphere that Earth will carry forward is not one inherited directly from the nebula. Instead, it is born largely from within, exhaled from volcanic vents, from the degazing of molten rock. Volcanic outgassing is the planet's first breath. As magma rises and erupts, it releases volatile compounds trapped within. Water vapor, carbon dioxide, nitrogen, sulfur dioxide, and other gases. These gases gather above the cooling crust, forming a dense, hazy atmosphere. At first, this proto-atmosphere is hot, heavy, and full of steam and ash. Clouds form, but they are clouds of mineral dust as much as water. The sky is not yet blue. It is a thick veil that traps heat and channels it back down to the surface, prolonging the planet's warm, molten state. But the outgassing also carries the raw materials for oceans. Water vapor, lifted into the atmosphere, cools and condenses as the planet's surface temperature slowly declines. Condensates fall as rain. Though at first, rain is more like torrents of steam turning back into liquid in a violent fashion. Over perhaps tens of millions of years, those rains fill low regions, building the first shallow seas. Oceans are not an instantaneous gift. They accumulate as a patient consequence of cooling, condensation, and continual delivery of water-carrying materials. Here, we must acknowledge another important source of volatiles: the steady rain of comets and water-rich asteroids. Jupiter, having gathered mass in the outer solar system, acts as both shield and slingshot. Its immense gravity shepherds smaller bodies, sometimes scattering them inward. Comets, icy and laden with simple organics, along with carbonaceous asteroids, contribute to Earth's inventory of water and volatile chemicals. Each impact reshuffles the surface and adds new material, sometimes delivering molecules that will later be important for chemistry that precedes life. Yet, early Earth remains under constant assault. Collisions are a defining motif of this young epoch. Some are small, leaving scars that will slowly be erased by later processes. Others are enormous. The largest of these collisions have the potential to reshape the entire planet. The final stages of accretion likely included a number of giant impacts. Catastrophic events in which a Mars-sized body strikes the proto-Earth. The most famous of these, which we will return to in later chapters, is the collision that led to the Moon's formation. For now, recognize that these impacts add mass, inject heat, and stir the planet's interior, prolonging periods of molten surface and resetting the clock for cooling. While this violent choreography continues, chemistry proceeds quietly. As rock melts and gases escape, chemical reactions shift the composition of the atmosphere and the forming crust. Minerals crystallize from cooling magma, locking away certain elements. Others remain in the fluid phase and are recycled through volcanic vents. The interplay between solidification and melting creates differentiation not only physically, core, mantle, crust, but chemically, setting aside reservoirs of volatile and refractory elements. These chemical reservoirs will later determine where water accumulates, where continents can form, and what materials are available at the surface for more complex chemistry. As Earth cools enough to allow persistent liquid water, the surface environment becomes more hospitable to further chemical complexity. The first oceans, shallow and warm, are excellent reactors. They mix dissolved minerals and organics delivered from beyond, reacting under the influence of minerals and the heat still coming from the interior. These early seas are dynamic. Tides pulled by the young moon, if the moon has already formed, or by other gravitational interactions, stir the waters. Waves lap at rocky margins. Hydrothermal systems along volcanic ridges pour mineral-rich fluids into the ocean, creating gradients in temperature and chemistry that are fertile ground for prebiotic chemistry. Beneath the waves, the mantle silently convects. Heat from the interior rises in slow plumes. Cool rock sinks toward the core. This convective motion is the engine that will one day drive plate tectonics. For now, the crust is mostly a patchwork of fragile, newly formed plates and basaltic plains. But in time, as continents grow from repeated partial melting and differentiation, more stable pieces of crust will persist longer, accumulating sediments and changing Earth's albedo and chemistry. These nascent continents will be reshaped repeatedly, but their existence begins to set the stage for longer-term surface evolution. Radiometric clocks, those precise measures of geological time, help us piece together this story. By measuring isotopic ratios in the oldest minerals and meteorites, scientists estimate the timing of core formation, crust solidification, and major impacts. These isotopic fingerprints show us that Earth's early history was rapid and intense. Core formation and heavy differentiation took place within tens of millions of years after initial condensation of solids. The final assembly into a single dominant planet took somewhat longer, though still rapid on cosmic scales. Yet despite the violence and heat, Earth's early evolution sets up several delicate balances. The retention of volatiles, water, carbon, nitrogen, depends on the timing and magnitude of impacts, and on how quickly the planet can cool and hold onto its atmosphere. The presence of a magnetic field and the accumulation of oceans are both pivotal. If the planet cools too slowly, or endures too many violent collisions late in its assembly, volatiles can be lost to space. Conversely, if enough water and organics are retained and mixed with the mineral world, the stage is set for chemistry of increasing complexity. Now let your thoughts slow even more as we consider the slower rhythms that follow this tumultuous youth. Over the next few 100 million years, the heavy bombardment that characterized Earth's infancy gradually winds down. The largest impacts become less frequent. The crust begins to stabilize in patches. The atmosphere matures as volcanic outgassing moderates, and as carbon dioxide is slowly drawn down by chemical reactions with rock and by dissolution into the growing oceans. The greenhouse effect of carbon dioxide helps regulate temperature, keeping the young planet warm enough for liquid water, despite a sun that was dimmer than it is today. And so gently, deliberately, the planet transitions from a molten, hostile world to a cooler, wetter one. The first long-lived crustal plates begin their slow dance. The mantle cools sufficiently to support sustained convective patterns. Oceans deepen and spread, sweeping across basins formed by the interplay of impacts and internal convulsions. The chemistry of the surface evolves, concentrating carbon, nitrogen, phosphorus, and other elements in places where they can interact more readily. Life is not yet present in our story here, but the chemical groundwork that will one day support life is being assembled, molecule by molecule, mineral by mineral. As we hover above this early Earth, take a moment to notice how many separate processes, some violent, some virtually imperceptible, are working together. Gravity sculpts form. Heat drives chemistry. Impacts reset the clock. Volcanic breath builds the atmosphere. The magnetic heart begins to beat. Oceans gather the planet's first liquids. Each process is slow on a human timescale and swift on a geological one. They intertwine, creating the complexity that will eventually support ecosystems and minds that can ask in wonder how they came to be. Before we close this chapter, it is worth returning to the theme of balance. The early Earth represents a delicate negotiation between destructive force and creative chance. Without the intense heat and violent collisions, core formation and the generation of a magnetic field might never have occurred. Without the gentler processes, cooling, outgassing, chemical weathering, no stable surface or ocean would form. The apparent contradiction is the heart of planetary formation. Creation through destruction, order through upheaval. So breathe once more, and imagine that glowing, roiling young planet shrinking into a calmer form. The last great impacts grow rarer. The magma oceans recede, leaving patches of solid crust. Storms of steam and ash subside into steady rains. Rivers begin to carve paths in the cooling rock. The stage is set for the long drama that follows. Oceans that hold chemistry, continents that rearrange, and the slow, patient emergence of life. But those are stories for later chapters. For now, let the image of early Earth rest in your mind. A world built from stardust, sculpted by collisions, warmed from within, cloaked in a restless atmosphere, and slowly, inexorably, finding its balance. We have walked a long way in time together, through heat and particle and pressure. Let these images guide you into a quiet place, where the next part of the story waits. Patient, inevitable and luminous with possibility. Settle back. Breathe slowly. Tonight we drift again through deep time, to a moment that changed Earth forever. The planet is still young, only tens of millions of years old. Its surface glows with fire. Volcanoes roar. Oceans of molten rock spread beneath a thick and hazy sky. And then, one of the most dramatic events in the history of our world unfolds. The birth of the moon. Around Earth, space is crowded. The solar system is still a place of chaos and collisions. Dozens of large protoplanets share unstable orbits, each pulled and tugged by the Sun and by Jupiter, the giant planet far away. Earth is larger than most of its neighbors, but it is not alone. Another body, nearly the size of Mars, circles nearby. Scientists call this body Theia. For millions of years, Theia shares Earth's orbital path, locked in a delicate gravitational dance. But the balance cannot last. Tiny shifts accumulate, orbits nudge closer, and eventually inevitability arrives. Earth and Theia are drawn together. Imagine the collision in slow motion. Theia approaches, an entire world hurtling through space. When it strikes, it does not destroy Earth, but it reshapes it completely. The impact is angled, a glancing blow rather than a direct crash. Theia's outer layers merge with Earth's, while much of its material is flung outward into orbit. For hours, molten rock and vapor swirl around Earth, glowing like a halo of fire. From that fiery halo, a ring of debris forms. Dust, molten droplets, shattered rock, all orbit Earth in a wide glowing disk. Over time, gravity gathers that material together, pulling clumps into larger bodies. These bodies merge again and again, until, at last, a single large companion emerges. This is the beginning of the moon. The new moon orbits close to Earth, much closer than today. It appears enormous in the sky, filling the horizon with its glowing presence. Tides in the young oceans are colossal, pulled by this nearby companion. Over billions of years, the moon will drift slowly outward. But in these early days, its closeness shapes Earth profoundly. The giant impact also stirs Earth's interior. The energy of the collision melts much of the planet again, resetting its surface. Heavy metals sink deeper into the core, while lighter elements remain above. The impact strengthens Earth's layered structure: core, mantle, crust. It also stabilizes Earth's tilt, giving our planet seasons and long-term climate balance. Without the moon, Earth would wobble chaotically, and life as we know it might never have thrived. And so, from destruction, creation, from collision, companionship, the Earth and Moon are forever bound, born from the same cataclysm. Two worlds sharing a single story. As you drift deeper into calm, picture the sky of early Earth. The air is hazy with steam and ash. The ground glows with rivers of lava, and above it all, a massive new moon hangs low and bright, its surface still molten, its glow reflecting the light of the newborn sun. a silent partner, born of fire that will one day guide tides, shape nights, and inspire every creature that gazes upward. Breathe. The fire is beginning to fade. The chaos that once ruled the young Earth now gives way to something quieter, something gentler. The world, once molten and scarred, begins to cool. Imagine drifting above this newborn planet. Below, the glowing seas of magma are slowly darkening, their surfaces crusting into solid rock. Steam hovers above them in great billowing clouds, thick and heavy, wrapping the planet in a dense, turbulent shroud. This is not yet the blue Earth we know. It is a red world, shrouded in mist and firelight, but change is coming. The intense bombardment that marked Earth's youth is easing. The great impacts grow rarer. The sky, once filled with streaking stones and fireballs, begins to calm. And in the stillness that follows, a transformation unfolds, one that will define the destiny of every future drop of rain, every breath of air, every living thing to come. The cooling of Earth is a long and patient story. As heat escapes into space, the crust thickens. The magma oceans retreat beneath it, glowing faintly through cracks and fissures. Volcanoes continue to erupt, but now they exhale something precious. Gases, carbon dioxide, water vapor, nitrogen, sulfur compounds. From within the planet's heart, its first true atmosphere begins to take shape. At first, this atmosphere is thick and stifling. The air would choke any life we know. It is heavy with carbon dioxide, rich in water vapor, laced with sulfur and ammonia. The pressure is immense, the heat suffocating. But this dense blanket serves a purpose. It traps warmth, slows the cooling, and holds close the ingredients that will one day make oceans and air. Now, imagine the rains. For centuries upon centuries, clouds gather and release. Lightning flashes through the darkness. Steam condenses, falls, and evaporates again. The rain hisses as it touches the still hot crust, vanishing into vapor, only to rise and fall again. But over time, as the surface continues to cool, the rain begins to endure. Drops no longer vanish. They pool, they collect, and soon they begin to carve paths through the rock. Rivers of the first water. The rains never stop. They fall for millions of years, filling the deepest basins, flooding the plains, shaping valleys and craters into oceans. Imagine that sound, the endless fall of water on stone. The earth is learning to breathe in cycles, clouds to rain, rain to ocean, ocean to vapor. The planet's first hydrosphere is born. These early oceans are unlike ours. They are warm, perhaps, near boiling in places, filled with dissolved minerals and metals from the newly exposed crust. They are green-grey under a red sky, rich with chemical energy. Here, the raw ingredients of life are dissolving and mixing. Carbon compounds, nitrogen, phosphorus, sulfur, all swirling together in a planetary cauldron of potential. The atmosphere above these oceans begins to evolve as well. Volcanic gases continue to pour forth, but slowly, reactions between air, water, and rock begin to draw down carbon dioxide. Some of it dissolves into the oceans, forming carbonates. Some is trapped in minerals within the crust. Each of these chemical steps helps cool the planet further, allowing more water to remain liquid. The balance between atmosphere, ocean, and rock becomes a self-regulating system, a primitive form of climate control. Above, the sun still burns fainter than it does today, about 70% of its current brightness. Yet, Earth does not freeze. The thick carbon dioxide and water vapor trap enough heat to keep the oceans liquid. It is one of the first great balancing acts of climate. A greenhouse strong enough to protect the planet from the sun's youth. Occasionally, the calm breaks. A massive asteroid still finds its way to Earth, striking with force enough to vaporize oceans and melt crust. For a moment, the sky glows with fire once more, but Earth recovers. Each cataclysm grows less devastating than the last. The planet is stabilizing. Beneath the surface, convection churns the mantle, creating slow-moving currents. Fractures form in the crust. Plates begin to shift. Primitive tectonic motion stirs, perhaps episodic at first, but persistent. Volcanoes rise, split, and sink again beneath the seas. Through this restless movement, the crust recycles itself, cooling and thickening with every cycle. The foundations of continents begin to take shape. Meanwhile, deep within the oceans, the story of chemistry unfolds in quiet detail. Along the ridges where magma meets seawater, hydrothermal vents erupt, black smokers belching mineral-rich fluids into the deep. Around these vents, complex chemical gradients arise, heat meeting cold, acid meeting alkaline. These are the crucibles where simple molecules begin to combine, break apart, and reform in endless cycles. Though life has not yet appeared, the stage is perfectly set. Above, lightning flashes through the storm-heavy sky, striking the surface of the oceans. Energy pulses through air and water, sparking reactions that build ever more complex molecules. Amino acids, sugars, simple organics. These are the alphabet of biology, written for the first time in the language of chemistry. Earth is cooling, but it is not cold. It is settling, but not still. Everything is in motion: air, water, rock, and energy, each element shaping the others in a delicate interwoven rhythm. The moon, bright and near, watches over this transformation. Its gravitational pull stirs the early oceans, raising tides that sweep minerals across the shorelines, mixing and remaking the chemistry of the surface. Tides are far greater than today, hundreds of meters high, roaring across the young seas. With every cycle, the ocean's chemistry evolves. Its complexity deepens. This dynamic balance between calm and chaos, heat and coolness, destruction and creation, is what gives Earth its character. It is not just a planet. It is a system alive with movement and feedback. Every eruption, every storm, every wave of rain contributes to the slow sculpting of stability. And in that stability, the impossible becomes inevitable. The planet has air, though it is still harsh. It has oceans, though they are alien and steaming. It has continents, though they are newborn and few. It has magnetic protection, atmosphere, water, and energy. All the essential ingredients aligned. Something extraordinary is about to happen. The Earth, once a world of molten stone, has cooled enough to dream. The time of chemistry is giving way to the time of biology. And so, as the rains quiet and the skies begin to thin, the next chapter of the story waits beneath the waves. Hidden, delicate, and full of promise, the story of life is about to begin. See, the storms have calmed, the fires have cooled, the planet now turns beneath a gentler sun, wrapped in clouds and oceans. The world that once burned is now blue. It is here, beneath the waves of this young ocean, that the next great transformation begins. Not of rock nor of fire, but of chemistry. For hundreds of millions of years the Earth has been preparing. Its crust has hardened, yet remains restless. Volcanoes breathe warmth and minerals into the sea. Lightning still flashes through thick clouds, splitting molecules apart, driving reactions in the atmosphere and on the surface below. The ocean churns with energy and raw potential. And within this restless sea, something stirs. Imagine the oceans of this time, dark green, heavy with dissolved iron and minerals, warmed by geothermal heat. Across their vastness, tiny islands of rock break the surface, steaming in the early light. Along the shorelines, waves lap against volcanic glass and basalt, leaving behind thin films of water that dry, then wet again with the tide. Each cycle concentrates the molecules that rain from the sky and pour from volcanic vents. Carbon compounds, amino acids, lipids and sugars, simple, yet rich with promise. These molecules are not yet alive, but they are restless things. They twist, join and fold. Some link into chains, polymers capable of holding structure, of storing information. Others form droplets, tiny bubbles of fatty molecules that trap water and chemicals inside. Within these microscopic bubbles, new reactions unfold, some random, some repeating, some becoming subtly organized. And somewhere, among trillions of such tiny worlds, something new happens. A reaction not only sustains itself, but replicates. It is a quiet moment. There are no witnesses, yet it changes everything. From that first self-copying molecule, perhaps RNA, perhaps something even simpler. The boundary between chemistry and biology dissolves. A new kind of matter appears. Matter that remembers, that grows, that evolves. Life. The first life is fragile, microscopic, single-celled, barely more than a shimmering droplet of chemistry wrapped in a membrane. It has no brain, no eyes, no voice. But it has one extraordinary trait. It can make more of itself. It can use energy from its surroundings, gather molecules, and replicate its own pattern. Each new generation carries the same design, yet with tiny changes, small errors in copying that create variation. Evolution, the quiet sculptor, begins its work. Imagine these first microbes drifting through the warm shallows, clinging to mineral surfaces, absorbing energy from chemical gradients. Some draw power from the reactions between hydrogen and carbon dioxide. Others from iron and sulfur near hydrothermal vents. The ocean floor is alive with invisible activity. Colonies forming near cracks where the planet's heat seeps into the sea. Minerals like pyrite and clay act as catalysts, guiding reactions, helping molecules link and transform. In these early ecosystems, the planet itself is a partner in life's creation. Rock, water, and chemistry work together. The Earth is no longer just a stage, it is an active participant. Slowly, life learns to harvest energy more efficiently. Some microbes develop primitive forms of metabolism, cycling elements between different chemical states. Carbon, nitrogen, sulfur. They form mats and biofilms that coat rocks and sediments. The sea floor becomes streaked with living color. Though invisible to the naked eye, it is an age of invisible architects, quietly shaping the chemistry of the planet. Among them, one lineage discovers something truly revolutionary, a way to capture sunlight. Photosynthesis. At first, it is simple. Bacteria using pigments to trap the energy of the sun and use it to build organic molecules. They release oxygen as a byproduct. At first, that oxygen reacts with iron dissolved in the oceans, staining the seas rusty red and forming vast deposits of banded iron that still exist in the oldest rocks today. But over time, the iron is used up, and oxygen begins to accumulate in the atmosphere. This event, the Great Oxygenation, will not arrive for hundreds of millions of years, but its seeds are planted here in these early oceans. Every tiny cell that releases oxygen is quietly reshaping the destiny of the planet. They are preparing the air that future creatures will breathe, though they will never know it. The rhythm of tides guided by the moon continues to stir the waters, driving cycles of concentration and dilution. Hydrothermal vents bubble and glow, rich in metals and energy. Volcanic islands rise and erode, their minerals feeding the sea, and through it all, life multiplies. Diverse, adaptable, persistent. Earth itself responds. The chemistry of the oceans shifts. Carbon dioxide is drawn down from the atmosphere, changing the climate, cooling the world slightly. Microbial mats begin to form shallow reefs, trapping sediments and building the first stromatolites. Layered stone structures created by colonies of living microbes. These fossils still exist today, ancient echoes of the first organized communities on Earth. From the chaos of chemical reactions emerges order, from randomness pattern, from matter memory. Billions of years before plants, animals, or humans, the planet is already alive with unseen kingdoms, tiny architects that breathe, feed and shape their world. Pause now, and imagine drifting over an ancient ocean 3.8 billion years ago. Beneath the surface, the water glows faintly with the shimmer of microbial life. You are witnessing the first living biosphere, a world that hums quietly at the molecular level. Life remains microscopic, but already it is shaping the planet's chemistry. Early microbes cluster in colonies, forming thin mats on the sea floor and along the edges of volcanic vents. These microbial mats are living laboratories, exchanging materials, stabilizing their environment, and creating complex chemical gradients that allow different types of metabolism to coexist. Some microbes depend on heat and minerals rising from the deep ocean crust, thriving where no sunlight can reach. Others learn to harness sunlight directly, evolving pigments to capture its energy. These primitive phototrophs, sun-eaters, mark the beginning of photosynthesis, a process that will one day power forests, coral reefs, and entire ecosystems. The earliest form of photosynthesis did not yet release oxygen. It used other chemicals, hydrogen sulfide, iron, or methane, as electron donors. But even this early innovation reshaped the planet's energy balance, allowing organisms to use light to drive metabolism. And then, somewhere between 3.5 and 2.8 billion years ago, a new version of photosynthesis appeared, one that used water as a source of electrons and released oxygen as a waste product. This was the birth of cyanobacteria. With this single evolutionary step, life began to transform the planet's atmosphere. The oceans, rich in dissolved iron, reacted immediately with the oxygen these microbes produced. The iron oxidized, forming solid rust that settled on the ocean floor. Over millions of years, these reactions built vast layers of iron-rich stone, banded iron formations that mark the first appearance of free oxygen. As the supply of dissolved iron ran out, oxygen began to accumulate in the air. Slowly, almost imperceptibly, Earth's skies began to change. What was once a haze of carbon dioxide and methane began to clear. The chemistry of the air shifted towards something new: oxygen. A gas that had never existed in abundance began to fill the atmosphere. The great oxygenation event had begun. For the early biosphere, this was both triumph and crisis. Oxygen, though essential to later forms of life, was a deadly poison to many of the planet's first microbes. Countless lineages perished, driven into extinction by the very waste product of photosynthesis. Others adapted, retreating into oxygen-free environments deep underground, or in sediments where the old chemistry still thrived. Yet, evolution always finds a way. Some organisms learn to use oxygen for their own advantage. It offered a far more efficient way to extract energy from food molecules. These were the ancestors of all aerobic life. Creatures that breathe oxygen, a lineage that would eventually lead, billions of years later, to complex cells, to animals, and to us. While biology was transforming the atmosphere, geology was responding in kind. The new oxygen reacted with volcanic gases, altering the climate. Methane, once abundant, began to decline as it combined with oxygen to form carbon dioxide and water vapor. The greenhouse effect weakened, and Earth entered one of its earliest known ice ages. Frozen oceans and glaciated continents reflected sunlight, cooling the world further. Even in the depths of these icy times, life persisted, anchored to the warmth of hydrothermal vents, sheltered beneath ice, thriving wherever energy and liquid water still existed. These ancient survivors became the seeds of every future form of life on Earth. From this long era of adaptation, complexity began to increase. Single-celled organisms diversified. Some developed internal membranes, dividing their cell interiors into compartments that performed specialized functions. This innovation, cellular compartmentalization, was a quiet revolution. It allowed for greater control over metabolism, and paved the way for the next great step, the emergence of eukaryotes. Eukaryotes are cells with nuclei, self-contained centers of genetic control. They evolved through one of the most remarkable partnerships in biological history, endosymbiosis. Somewhere in the ancient oceans, a large primitive cell engulfed a smaller one, but did not digest it. Instead, the smaller cell took up residence inside, continuing to live and divide within its host. Over time, the partnership deepened. The internalized cell provided energy through aerobic respiration, while the host offered protection and nutrients. The two became inseparable. The internal symbiont evolved into the mitochondrion, the power source of all complex life. A similar alliance occurred later with cyanobacteria, giving rise to chloroplasts, the green engines of photosynthesis inside plants and algae. Through these acts of cooperation, Earth's biosphere gained the potential for multicellularity, for greater energy flow, and for biological diversity beyond anything that had existed before. For nearly 2 billion years, life remained primarily microbial, invisible to the naked eye, yet profoundly influential. It sculpted the atmosphere, stabilized the oceans, and changed the chemistry of rocks themselves. Microbes formed reefs, cycled nutrients, and maintained the balance between gases that would later sustain animals and plants. The surface of Earth became biologically active in every corner. Oceans, mudflats, sediments, and even deep within the crust. By around 1.8 billion years ago, oxygen levels had stabilized at a fraction of what we breathe today, enough to support complex single-celled life and prepare the stage for what was coming next. With the planet's chemistry transformed and the atmosphere breathable, the groundwork for multicellular organisms was in place. The planet was no longer just alive, it was self-regulating. The biosphere, hydrosphere, and atmosphere had become parts of a single interconnected system. Climate, chemistry, and biology worked in feedback with one another. The Earth was learning in its own slow way to sustain balance. And from that balance, new possibilities would soon emerge. Cells would begin to cooperate. Communities would evolve into organisms. Complexity would rise again as evolution continued its patient work. The next chapter in the story of our planet would be one of union, symmetry, and the rise of form, when life learned to build itself into visible structures and the first multicellular creatures began to appear in the ancient seas. The world is no longer silent. The oceans whisper with the activity of countless single cells. Bacteria, algae, and protozoa, drifting through light and darkness. For more than 2 billion years, these small and simple beings have ruled the planet. They have shaped the air, tempered the seas, and turned bare rock into fertile ground for the future. But evolution never stands still. In time, even simplicity begins to experiment with cooperation. Some cells remain solitary, floating freely through the water. Others begin to live in clusters, colonies that share nutrients and divide labor. At first, these clusters are loose, each cell independent. But small advantages begin to appear when they stay together. Groups can grow larger, move with more force, and survive longer in turbulent seas. Natural selection begins to favor cooperation over isolation. Within these clusters, cells start to specialize. Some handle feeding, some focus on reproduction, some take on structural roles, giving shape and stability. What began as a collection of identical cells becomes something new. A single organism made of many parts. Multicellularity has arrived. At first, these multicellular forms are simple. Filaments, sheets, or hollow spheres, barely visible to the eye. But their appearance marks a turning point in Earth's story. With specialization comes complexity. With complexity, innovation. The oceans of the Proterozoic Eon, around 1 billion years ago, are filled with life that is mostly soft-bodied and slow. Algae grow in the shallows, turning sunlight into food and releasing oxygen into the air. Stromatolites, the layered structures built by microbial mats, still rise like living fossils in coastal waters. But new shapes are beginning to emerge. Ribbons, discs and fronds of multicellular organisms that drift and sway in the currents. These are the ancestors of plants and animals alike. Beneath the surface, oxygen levels continue to climb. The atmosphere now contains enough of this reactive gas to fuel larger, more energetic forms of life. Metabolism can quicken. Movement becomes possible. The quiet chemistry of the early biosphere begins to accelerate. By around 800 million years ago, the oceans witness an explosion of innovation. Algae evolve into complex forms, red, green and brown lineages that will one day populate coral reefs and forests. Some eukaryotes develop flexible cell membranes and internal skeletons, allowing them to engulf food and move in deliberate ways. The groundwork for animal life is being laid cell by cell, trait by trait. And then, as if the planet takes a deep breath before the next leap, the climate shifts. Ice creeps across the continents. Glaciers grind the land down to dust. This is the time of the Snowball Earth episodes. Global-scale glaciations that may have frozen even the equatorial seas. For millions of years, sunlight reflects off white ice, cooling the world further. Oceans beneath the ice remain liquid in places, sustained by geothermal heat. And within them, life endures. Slow, hidden, but unbroken. These icy ages are not merely interruptions. They are catalysts. The cycles of freeze and thaw reshape the chemistry of the oceans, filling them with nutrients washed from the land as the glaciers retreat. When the world warms again, oxygen and minerals flood the seas. Life responds with vigor. Around 600 million years ago, the Ediacaran period begins. For the first time, the fossil record shows a menagerie of soft-bodied creatures unlike anything before. On ancient seafloors, frond-like organisms anchor themselves in sediments, absorbing nutrients from the water. Disc-shaped forms ripple across the mud. Some are simple sheets of tissue. Others bear traces of symmetry, hinting at the future designs of animals. They leave impressions in the sand, faint, mysterious patterns that speak of a world coming alive with form. These are the Ediacaran organisms, the first truly multicellular life visible on Earth. Their diversity is astonishing and puzzling. Some resemble plants, others jellyfish, others nothing known today. They live in a world without predators, where competition is gentle and movement is slow. Energy comes from sunlight filtered through shallow seas, from microbes living in symbiosis, or from the chemistry of the ocean itself. Yet even in this tranquil setting, evolution experiments relentlessly. Some creatures begin to move, gliding slowly across the seafloor, leaving delicate trails behind. Others develop internal channels to circulate nutrients more efficiently. The first muscles, nerves, and tissues are emerging in primitive form. The rise of these organisms changes the seafloor ecology. Sediments once bound by microbial mats are now disturbed by movement. Oxygen penetrates deeper into the mud, creating new habitats. Predation, once non-existent, becomes possible, setting the stage for arms races that will drive rapid evolution. By the end of the Ediacaran, the rules of life have changed forever. Cooperation and structure have produced bodies capable of sensing, moving, and interacting. The biological stage is ready for a burst of innovation unlike any before. As the next era begins, the Cambrian period, the oceans will fill with shells, skeletons, eyes and limbs. The world will awaken in color and motion. But for now, in the fading glow of the Proterozoic seas, the first multicellular creatures drift softly, unaware that they are the architects of everything to come. The long silence of deep time begins to break. For billions of years, life has whispered in the language of microbes and single cells. In the Ediacaran seas, it began to murmur in soft-bodied forms and simple colonies. But now, around 541 million years ago, the whisper becomes a chorus. The Cambrian period dawns, and with it, the world comes alive with shape, structure, and motion. At first glance, the oceans seem unchanged. The continents lie low, clustered near the equator, bathed in warm sunlight. Shallow seas flood the margins of the land, rich with oxygen and nutrients washed from eroding mountains. It is here, in these sunlit waters, that evolution finds new freedom. The quiet organisms of the Ediacaran world fade, replaced by creatures that move, burrow, hunt and build. The sea floor, once a soft, undisturbed plain, becomes a battlefield of innovation. For the first time, animals develop hard parts, shells, spines, and exoskeletons that leave a fossil record written in stone. It is as if nature has discovered engineering. The Cambrian explosion is not a single event, but a cascade. A series of evolutionary breakthroughs unfolding over tens of millions of years. In this brief geological moment, nearly every major animal body plan appears. Arthropods, mollusks, worms, chordates. The blueprints of all future creatures, of crabs and fish, birds and mammals, even humans, are drawn here. At the center of this explosion is predation. Before the Cambrian, few creatures hunted, but now, with increased mobility and sensory complexity, the first predators emerge. Eyes evolve. True, image-forming eyes made of crystal lenses. Jaws, claws, and armor soon follow. Every innovation by one species becomes a challenge for another. Evolution accelerates into an arms race. In the warm shallows, trilobites scuttle across the sea floor, the most iconic of Cambrian life. Their jointed legs and compound eyes give them agility and awareness never seen before. They graze, burrow, and migrate in vast numbers, leaving intricate tracks in the sediment. They are among the first animals with a nervous system capable of coordination, and they dominate the oceans for 250 million years. Nearby, strange forms drift and dart through the water. Anomalocaris, the unusual shrimp, glides like a segmented torpedo, eyes perched high on stalks, grasping limbs poised to snatch prey. At over half a meter long, it is the apex predator of its time, a terror to smaller, softer creatures that have never known fear until now. Other organisms evolve new defenses in response. Some grow spines or shells made of calcium carbonate. Others burrow deeper into sediments or adopt camouflage. Still others form colonies, safety in numbers. Every adaptation triggers another, and the feedback between predator and prey drives complexity faster than ever before. The Cambrian seas are a mosaic of life. Worm-like burrowers sift through mud for nutrients. Sponges filter seawater through intricate channels. Brachiopods and mollusks anchor to the seafloor, opening shells to feed. Tiny plankton drift in the upper waters, feeding the entire ecosystem below. And among them swim the earliest chordates, small, flexible-bodied animals with a primitive backbone, precursors to all vertebrates. In places like Burgess Shale, now a fossil-rich mountain in Canada, time has preserved this explosion in exquisite detail. Soft tissues, eyes, gills, even digestive tracts are frozen in black shale, recording a world of forms unlike anything alive today. Here we see creatures like Opabinia, with 5 eyes and a long trunk-like appendage. Hallucigenia, walking on spines like a dream creature. And Wuaxia, armored with scales and bristles. Each represents an experiment, a different way of building an animal. Beneath the strangeness, there is order. The foundations of modern biology are being established. Complex nervous systems, circulatory systems, and digestive tracts evolve. Muscles coordinate with skeletons. Eyes send images to primitive brains. The architecture of behavior itself, the ability to sense, decide, and act, is taking shape. This new level of complexity transforms the entire planet. Burrowing animals churn the seabed, oxygenating sediments and recycling nutrients. Photosynthetic plankton fill the upper oceans, pumping oxygen into the atmosphere. The biosphere becomes dynamic, self-regulating, and interdependent on a scale never seen before. The Cambrian explosion is more than an increase in diversity. It is the birth of ecological interaction. Food webs, niches, symbiosis, and competition all appear in their recognizable forms. Evolution has moved from chemistry to cooperation, from isolated species to systems. By the end of the Cambrian period, around 485 million years ago, Earth's oceans are teeming with complex life. Every major ecosystem type, reefs, open water, benthic plains, is alive with motion and color. The evolutionary foundation for all future life is now in place. The world that began in volcanic fire and chemical chaos has become a living planet of senses and structure. The next great chapter will move from the sea to the land, from water to air, from gills to lungs, from fins to feet. Life is preparing to walk. The seas have become crowded. By the end of the Cambrian, the oceans teem with complexity. Trilobites, mollusks, corals, and primitive fish-like creatures, all thriving in ecosystems that pulse with energy. But evolution, relentless in its curiosity, is about to test a new frontier, the world above the waves. The Ordovician period begins about 485 million years ago. Continents drift slowly across the globe, clustered mostly in the southern hemisphere. Shallow seas flood their edges, rich in life and light. New species continue to emerge, and coral reefs, built by colonies of tiny animals, begin to rise from the seafloor. The ocean becomes more structured. Layers of plankton, swimmers, and bottom dwellers forming the first true marine food webs. In these waters, the first jawless fish, or agnathans, appear. They are small, armored with bony plates, gliding through the currents by undulating their bodies. Though primitive, they represent the beginning of the vertebrate lineage, the ancestors of sharks, amphibians, and humans alike. The invention of a backbone, even in its simplest form, changes everything. It provides strength, flexibility, and the potential for growth in size and complexity. While animals dominate the sea, the land remains barren. Silent plains of rock, sand, and stone. But even here, life is beginning to take hold. In damp cracks and tide pools along ancient shorelines, microbial mats creep outward. Lichens, partnerships between fungi and photosynthetic algae, begin to colonize bare rock, slowly breaking it down into soil. From these humble beginnings, the first plants will rise. By around 470 million years ago, the earliest land plants appear. Tiny, moss-like organisms without roots or leaves, clinging to moist ground near rivers and lakes. They breathe in carbon dioxide and release oxygen, spreading across the continents in a thin green film. These pioneers are simple, but their impact is immense. By stabilizing soils and drawing down carbon from the air, they begin to reshape the atmosphere and climate. As plants spread, they invite new forms of life to follow. Insects' ancient ancestors, arthropods related to millipedes and centipedes, venture onto land, feeding on decaying organic matter. For the first time, animals breathe air, walk on solid ground, and explore a world without buoyant seas to support them. Evolution faces a new set of challenges: gravity, desiccation, temperature, and exposure to sunlight. Each obstacle becomes an opportunity for adaptation. The Silurian period follows, around 443 million years ago, and the green tide of life expands. Vascular plants evolve, plants with internal tubes that carry water and nutrients, allowing them to grow taller and farther from water sources. Simple roots anchor them into the soil. Leaves unfurl to catch sunlight. The land begins to bloom with the first primitive forests of club mosses and ferns. The atmosphere grows richer in oxygen, feeding new possibilities. Insects diversify. Millipedes and scorpion-like creatures grow to impressive sizes, breathing the thick, oxygen-heavy air. The continents turn from bare rock into living landscapes, crossed by streams, shaded by spore-bearing plants, and buzzing with early terrestrial life. But the greatest transformation is still unfolding in the water. The Devonian period, the age of fish, arrives around 419 million years ago. In the seas, vertebrates diversify spectacularly. Jawed fish evolve, giving rise to sharks and armored placoderms, apex predators of their time. Their jaws allow them to bite, chew, and hunt more effectively than ever before. Fins become stronger and more versatile, enabling better control and speed. Among these evolutionary experiments are a few remarkable forms. Fish with fleshy, lobed fins supported by internal bones. These fins can push against the seafloor, propelling the animal forward in shallow water. In them lies the blueprint for limbs. Rivers and coastal lagoons of the Devonian world become laboratories for innovation. Plants line their banks, stabilizing soils and filtering sunlight through their fronds. Insects crawl along the mud. Amphibian-like fish creep into the shallows, gulping air from the surface when oxygen in the water runs low. Over generations, their fins grow stronger, their lungs more efficient, their ribs more supportive. From these transitional creatures, known as tetrapodomorphs, the first amphibians emerge. They are not yet masters of the land, but explorers of its edges. They wade in and out of water, hunting insects and small crustaceans, laying their eggs in the shallows. They are the pioneers of the vertebrate conquest of land, the ancestors of reptiles, mammals, and birds. The Devonian world hums with energy and transformation. Coral reefs flourish, teeming with life. Forests spread across the continents, drawing down vast amounts of carbon dioxide. The air fills with oxygen, and global temperatures begin to cool. Yet this very success brings instability. Nutrients from the expanding plant life flow into the oceans, fueling algal blooms that deplete oxygen and trigger mass extinctions. Life flourishes, then falters, in a cycle of creation and renewal that will echo throughout Earth's history. By the end of the Devonian, about 359 million years ago, the continents are green, the air is breathable, and vertebrates walk on land. The planet that once belonged only to microbes and fish now echoes with the quiet stirrings of forests, the rustle of leaves, and the soft crawl of creatures taking their first steps into a new world. The age of terrestrial life has begun. The next chapter will bring forests that darken the continents, insects that fill the skies, and giant reptiles that will dominate for ages to come. Life has claimed the land, and soon it will claim the world. The world has changed beyond recognition. The oceans that once ruled the planet are no longer its only domain of life. Forests stretch from horizon to horizon. Towering club mosses, ferns, and horsetails forming dense jungles that thrive in the thick, humid air of the Carboniferous period, more than 300 million years ago. The air itself is rich in oxygen, nearly double today's level. Fires burn easily, insects grow huge, dragonflies with wings wider than a man's arm, millipedes longer than a car. The earth feels alive in a way it never has before, heavy with breath and green growth. Within the swamps and forests, a new kind of creature takes shape. The amphibians that once lingered at the water's edge begin to evolve tougher skin, stronger limbs, and eggs that can survive on land. These are the first reptiles, the pioneers of a new independence, no longer tied to water. They can wander far from lakes and rivers, exploring the vast interior of the continents. In them lies the seed of future empires, the dinosaurs, the mammals, and humanity itself. The continents themselves are moving too. Over millions of years, tectonic plates drift and collide, assembling into a single supercontinent, Pangaea. It is a world of extremes. Endless deserts in the interior, lush forests along the coasts, and mountain ranges rising from the crushing of ancient seabeds. The climate swings violently from hot to cold, wet to dry, as the great landmass changes the balance of air and sea. Evolution keeps pace, sculpting life to fit every shifting condition. But balance is fragile. Around 252 million years ago, deep in the Permian period, Earth faces its greatest trial. Volcanic eruptions in what is now Siberia pour out fire for millions of years. The air fills with carbon dioxide. The oceans turn acidic, and global temperatures soar. Life struggles to survive as ecosystems collapse. More than 90% of species vanish. The greatest mass extinction in the planet's history. Forests wither, coral reefs crumble, and even the air grows still. Yet the story does not end there. From the ashes of that devastation, life begins again. The survivors, small reptiles, burrowing creatures, simple plants, slowly rebuild the biosphere. In the next age, the Mesozoic, the descendants of these survivors will rise to astonishing heights. Dinosaurs will rule the land, flying reptiles will claim the sky, and mammals will bide their time in the shadows. The planet will heal itself as it has before and begin again. Across billions of years, Earth has transformed itself many times over. From dust and gravity, it became a planet. From fire and stone, it built an atmosphere and oceans. From chemistry and chance, it gave rise to life. From survival and adaptation, it built forests, continents, and thinking creatures who now look back and wonder how it all began. The story of Earth is not a straight line, but a rhythm, a vast, slow heartbeat of creation and renewal. Every extinction clears the stage for a new act. Every catastrophe seeds the next beginning. The continents will continue to drift. The seas will rise and fall. Life will change, vanish, and bloom again. The planet endures, and so when you look up at the moon, the silent witness born from Earth's earliest fire, remember that it too carries the memory of every chapter. The dust of its surface, the pull of its tides, the rhythm of its orbit. All are echoes of the same cosmic dance that began with a cloud of gas and dust around a newborn star. Earth is not finished. It is still becoming, and somewhere, in the whisper of wind, in the shimmer of water, in the quiet turning of the planet beneath your feet, that ancient story continues, patient, endless, and alive. This is the world that was born from stars, and this is where the story begins again. Now the world is quiet. The ages of fire and ice have passed. The forests have risen and fallen. The oceans breathe in slow tides beneath a sky lit by the same sun that watched over the first grains of dust. and from the remnants of everything that came before. From molten stone, from ancient seas, from the long patience of evolution, we emerged. We are the children of this planet. Every atom in our bodies was forged in stars that lived and died long before the sun was born. The calcium in our bones, the iron in our blood, the oxygen we breathe, all once drifted through the cosmos as stardust. The universe did not give us life as a gift. It grew us slowly from its own dust and fire. We are, in a quiet and literal sense, the Earth made conscious. Through us, the planet that once was molten and silent has learned to look up, to think, to dream. When we gaze at the moon, we are the same planet that once collided with Theia, now watching its own reflection in the sky. When we wonder where we came from, we are the cosmos remembering itself. The story that began in darkness has become one of awareness. It is still being written in every heartbeat, every wave, every spark of thought. The continents continue to drift. The sun still burns. The future is unwritten, but the lineage of wonder endures. We are the storytellers of a planet 4.5 billion years in the making. We stand at the edge of deep time, looking back across the ages and forward into the unknown. And somewhere, far away, the same process begins again. Another cloud of dust, another star, another world waiting to wake. For in the end, every story of Earth is a story of the universe, and every breath we take is a memory of the stars.